Everybody their day.
Please hustle up with the warm-up. Then take out your 7.1. And you'll almost certainly want another sheet of paper for notes.
Oh, really? There's a lot of stuff. If you don't, you get 0 credit.
No, just the asset.
I'm just going to run to the library then.
That just sucks. I don't want to do it.
It's awesome. We talked to your dad about the thing. No, not yet. I will today. I'll let you know. You want to start this weekend? Start putting it on Monday.
Oh my god, it's safe paper. They came out past today, sorry.
So crunchy and delicious.
It like, I don't understand what water.
I don't like it. I don't like it at all. I feel like I'm the only person
I don't
that doesn't
understand
like
what
it.
it is.
It's a
So you
root.
eat it.
It's a red.
What is it?
It's white,
vegetable.
crunchy.
It's just like a potato.
It's like
It's like
all.
Asian pear. Yeah.
It
Okay, so that.
has that like kind of starchy, watery white, but it's not nearly as soft and it's not nearly as sweet.
It's really, what is it? I don't like it.
It literally tastes like water.
Yeah, it's like
But it's sweeter.
crunchy water glory.
I hate it.
It's so good for you.
Really?
Sorry, hydrate.
Aside from drinking water.
It's got like vitamins and stuff.
It's probably like cucumber. Yeah. It's
Vitamin, like
Important ones.
the hiccup of vitamin.
Just
You're the one wondering.
I heard Waterhouse is pretty healthy for you too.
What did he eat out over in Japan?
Okay. Anybody need their homework stamped because they were absent yesterday? Anybody have any questions about the homework assignments in this unit? Remembering that you have the Carl out of the future due a week from today. Does anybody have any questions, challenges, ways I can help you with your group, reaching them, communicating, figuring out who they were? I don't want that. Any other miscellaneous conversation about Unit 6, 7, finals, planning, looking ahead? This is the part I don't get is. Did we finish the elements of passive solar design yesterday?
Yep.
Yeah.
Did I recommend that you do all 10 even though you only need 8 technically? Oh, there's a term I'd like to throw out for convection. You might want to search solar chimneys. I'd like to start assignment 7.1 today if there's no other questions. With the vocab first. But like I said, you'll almost certainly want another piece of paper. I'm pretty sure you'll definitely want another piece of paper. There we go. First in the vocab. Stop me if you have a question. Energy is the ability to do work. Work is a force applied over a distance. The first and second laws of thermodynamics get infinite stars because they're on every AP test and they come up forever. Yeah.
The first law.
Yeah, and I have a couple of things to tell you about the laws of thermodynamics. The first, energy is neither created nor destroyed, it just changes form. It's neither made nor lost. And you'll notice, it may be worth putting in your notes, that the first law of thermodynamics is about the amount. It's a question of quantity. The implications of that are actually kind of mind-blowing, considering that the universe has like a known and fixed amount of energy and stuff. That's like kind of amazing. And there's an acronym that I'd like to throw out there. It's written on the board. It says TINSTAFL. In the world of politics, this is a slightly loaded concept. Does anybody know the politics of this? Yeah, this is for the first law of thermodynamics, like quantity. Does anybody know the politics of TINSTAFL? Anybody know what it stands for? Really? That's okay. There is no such thing as a free lunch. There is no such thing as a free lunch. And we'll start with the politics. In a famous debate about providing food for the poor, politicians were arguing about the merits of giving people free food. And some politician goes, "You're all crazy. This is all make-believe. There is no such thing as a free lunch." Their point being, someone has to pay for it. Politically, this was a debate about how much taxes are used for public services. The point being, well, if you're giving Cedar a free lunch, well, you know, Lexi had to pay the taxes that bought the lunch to give that kid, so it's not a free lunch, it's coming out of someone else's pocket. And economically, this was a very compelling argument. The government does nothing for free. But in terms of energy, you have to remember, you don't get energy. You're just picking up where it was left off. There is no making energy. You can gather, you can focus, you can pile up, you can transform, but you can't really make energy as we understand it now. I mean, we can't. Are you smirking at me, young man? Are you smirking at me?
Well,
We don't want to start this debate about making energy? Go ahead, hit it, bro.
anything's possible. Well, everything in the universe came from somewhere, and there's energy in the universe, so that's like being like, well, I mean, yeah, you can't make energy now, but you could have made energy at one point in time, and energy was made at one point in time.
Yeah. but we certainly can't make it. The second law is about quality. When energy changes form, some quality is lost. And we've already defined quality, haven't we? How much work you can do, how focused or concentrated the energy is. We'll come back to that question later. So remember, you might want to write it in there. First law, quantity. Second law, quality.
So when you lose the quality, there's still a lot more quantity?
The quantity is the same. So, if you measure the calories in the electricity, that equals the quality of the calories of light plus the calories of heat. Neither of those is the same quality. The quantity adds up, the quality has gone downhill in that transformation. Electrical resistivity. Anybody know what this means? Had physics? What is resistivity or resistance? Come on. What?
The friction of electrons when it goes through a conductor.
You have the right idea. Technically it's not friction, technically it's not electrons. Yeah.
It's like how much electricity turns into heat when you run it through time.
Yeah. Electricity doesn't travel freely. All substances waste some of the electricity going through them. There's these things called hyperconductors. They have very low resistivity. They are substances which the electricity travels through pretty well. As compared to like a copper wire, that wastes a lot of the electricity. Electricity gets pushed in one side, the amount coming out is less because there's been heat along the way, energy loss. Because you're like squeezing through. You can imagine running through a crowd, that's resistivity. If you line up the crowd, there's a little less friction, but no matter what, you're going to have to slow down a little. Running through a crowd, resistivity, are we okay with that? Energy efficiency was today's warm-up. Can anybody write that as an equation? Energy efficiency as an equation. I'm waiting.
Output divided by input.
Yeah, it's on the whiteboard. Like how much of the energy you put into something comes out as the intended output. So like of the electricity that goes into a light bulb, how much of that makes light? And just so you know, for a screw-in light bulb, that's about 5%. What happens to all the other energy? Lost is heat. Inefficiency is the heat in the system. So look, there's two ways to describe this. You can do it as a ratio of output to input, or as output divided by input. So you'll either get a ratio, like 1 to 5, or you'll get a percentage, like 20%. And remember, energy efficiency, at least in these terms, is about the amount. This is first law efficiency. We're going to come back to that. Would anyone like to ask me anything about any of the vocab before we start to look at the study goals? Bueller, anyone? Yes?
Back to the electrical resistivity.
Uh-huh.
I thought you said that like wires help it and power lines help it like let electricity move faster. Like it pushes it along. So you said the crowd thing, which slows it down.
Compared to traveling through air or wood chips or something, wires are way better. But, like all substances which transmit electrical charge, some amount is lost. Now, number 9 I'm willing to skip unless you had a question. A few fun facts about ancient energy stuff. But number 10 is 3 stars. The terminology in number 10 is absolutely critical, and to anybody who speaks physics, it's totally fundamental and basic. Kinetic energy, chemical energy, potential energy, maximum potential, electric and static energy. Light, sound, waves, all that stuff. We've got a problem. Most of us totally understand the concept, right? If I let go of this marker, it will fall, right? So right now it has potential to fall. Everybody got that? Potential energy, potential kinetic. It's going to move. Are we cool with that? And then do we all realize that now it has more potential energy because now it will fall further and thus faster? Everybody got that? And if I turn it that way, it's going to have less air resistance. So technically, by turning it that way, I've slightly raised its potential energy. Everybody got that? And at some point, don't you all feel like, wait, we're all just looking at a stupid marker. It's the same marker that it's always been. And how did the marker change in any way? It's the same marker. And that energy is just a function of this system. And all of a sudden, we're all just like looking around, making all these words about a stupid marker. And we're just like a bunch of idiot children, like transfixed, staring at a marker. Anybody ever had that experience when you talk physics where everything makes sense and all of a sudden you realize we're just talking about like nothing? Like, I don't know if you've ever had that experience, but I sort of struggle with that a little bit. Like, I was a good physics student in high school. I took AP Physics. I was in the honors physics series when I entered the university. Because I'm a scientist, I was pretty aggressive about my science courses, and I was like really proud of getting good grades in my physics class. I always thought like everything always made sense. But I always had this experience, kind of like when you realize that you're like really close to falling off the edge of something, like, whoa, we're just talking about nonsense. And I think that's one of the big challenges in physics, that you have to like try to stay engaged in the conversation, because as soon as you like look around, you realize, wait, this is all just BS. This is all BS.
That's just school.
Yeah, and seriously, like I feel, that I say this every year when I have this conversation. I think that's where we lose a lot of students in education. Everybody looks around and goes, wait, what are we doing here? This is stupid! Then everybody ditches to go get pregnant or smoke pot in the parking lot or something. Maybe at the same time. Go, Paul! Paul's like, I'm out of here! Why are you out there? Which one? Kayla? I gotta warn you that thing about like potential and kinetic and heat and energy quality and low grade and high grade, it's not supposed to trick you. It is supposed to be a way that we understand fundamental laws of the universe. And sometimes, like if you get too deep in the wormhole and you feel like you're just babbling, you might want to just take a little breath and step back and try to remember how you got there. Some of you don't really struggle with this, like physics-minded people, abstract thinkers, like no big deal. Some of us, you kind of gotta like shake yourself a little bit, make sure you get back on track. Y'all know Melissa Woods? Miss Woods?
Yeah.
Teacher on campus? she happens to be like one of the most gifted and talented educators in the history of teaching, and like one of the coolest humans that I work with, and like she's like really good at this. If anytime in this chapter you get to that, or in this unit, you get to that point where you're like, wait, what the hell are we talking about? And you just can't make it all click again. It's like you take apart all the parts of a watch and then you realize, like, what the hell am I going to do with it? Like, if you can't make it all fit together again, I would recommend that you maybe just try to hit her up real quick. She's super accessible and like really friendly. And if you're just like, I can't make the pieces fit, she'll be like, oh, let me help you with that. She's really good at it. I, on the other hand, am not. Do we all know how to describe energy quality? How focused it is, how concentrated, how much work it can accomplish? We're good at that? Because if we are, I'm about to start number 11, which is another 3-star goal. And anybody want to ask me questions, this would be the right time. Yes, begin to tell.
What is low-grade heat energy?
It is what we might consider the lowest quality. It is the fizzle at the end of energy quality. It can do basically no work. Like if it is just marginally hotter than its surroundings, that's like the end of the energy spectrum. Does that make sense? Low-grade heat, that's the weakest energy there is. And by the way, the mind-boggling fundamental conundrum here is that given these very simple laws of the universe that we just set up earlier, the entire universe energy budget is tending toward nothingness, like zero value. Like all energy is tumbling downhill to just fizzle out as heat. So at one point, a little while ago, all the Earth's matter and energy were compressed into something maybe the size of a golf ball, but obviously a lot heavier. And the laws of like particles and atomic structure wouldn't allow that for very long, so it went, and that was the Big Bang. And it probably didn't make any sound, but who knows? Yeah?
What's an end use?
Explosion.
And all that energy goes, expands, and you get like universal expansion and light and like star formation. And ever since then, all the energy's been fizzing out, and someday the universe will stop expanding, and the light will like stop shining. Everything will go like, and all the energy will be spent. And then what? So there's one theory that says like universes come back. that the universe comes back together and recompresses, and we get like endless cycling of more and more Big Bangs. Of course, there's separate ideas now that we know about antimatter and dark energy. And just so you know, these are like the mind-boggling wormholes where like geniuses spend 60 years of their lives like sharpening pencils with fellow nerds. Anyway, low-grade heat energy, that's the end. All energy ends up as low-grade heat energy. It's like the lowest quality possible. Yeah?
What's chemical potential?
It's the potential energy trapped in chemical bonds. So it's things that can react to release energy. It's one way of measuring what can happen given chemistry in the system. So like coffee has chemical potential because that caffeine in Jose's body will generate a certain amount of energy with whatever chemistry can happen in my body. So in a given system, given chemistry, what energy is going to come out given these ingredients added? Anybody else? Yeah?
What units do we use to describe energy quality?
I'm not sure. Does it have units?
Are there units?
Oh, for quality, I don't know. I mean, is it per unit volume? Like, how do you measure energy per
It
volume?
would be like work per unit mass or something like that.
Yeah, maybe. I'm curious too. I've always thought it's slightly more esoteric than that. And so I've never heard of a unit for it, if that answers your question. I know how we measure energy, the whole like BTU, joule, calorie, kilocalorie thing. But I've never heard of a like volume measure. Like when we say concentrated, I'm like, what do we like per square foot?
You know, when I did the stuff on coal in 7.3 was like, there was like the higher quality coal and the lower quality coal, and it was based off of like energy per kilogram of coal. So does that mean it's higher quality energy in this sense as well?
I think so. Yeah, I think so. Okay. So number 11, 3 stars. First law and second law. The end use is sort of the intended outcome of your system. Got it. So like end use of light bulbs is making light. Does that make sense? Number 11 gets 3 stars because there's actually 2 types of efficiency. We talk about efficiency as one thing in our modern day-to-day lingo, but there's actually 2 types of efficiency. There's efficiency number 1. Please look up this kind, which is the amount. That's first law efficiency, and that's a term you got to know. First law efficiency, because we're describing amount. We're describing quantity of energy.
So first law efficiency is the amount.
Yeah, first law efficiency is the amount, right? So when people talk about like how efficient is your car, that's what they mean. Which amount? Just so you know, your car is about 10% efficient as a way of translating chemical potential into moving stuff. These light bulbs, I think they're about 13% efficiency. So of 100 calories of electricity, 13 calories are light and 87 calories are heat. We don't measure light in calories very well. But there's this thing called, oh yeah? What can you call? You're raising your hand?
Yeah, maybe you're still getting it.
But there's this thing called second law efficiency. Can anybody imagine how there could be an efficiency in the quality of energy? Yeah.
Like, if you're putting power into like a heater, and then all your energy is going into heat, then you have really, really bad second law efficiency, because like the usability of that energy goes from like really high electricity to like really unusable heat.
Yeah, that's pretty much right there. Yeah. And for students who maybe didn't catch that, I can try to give you some numbers to clarify what he says. If you put energy into a heater, that's really second law inefficient because you've used something of very high quality, the energy going in, to make something of very low quality, just plain old crap heat that's not really useful for anything. You understand what I mean by that? High quality to low quality, that's inefficient. And if you don't understand, let me give you some numbers and maybe this will explain it better. How many of you have a natural gas heater in your house, like a furnace? Like some sort of delivered hot air? You probably don't realize that, but almost all of you do. I did my research. Check this out. Natural gas burns at a temperature of 1,832 degrees if it's clean combustion. 1,832 degrees. That's really hot. 1,832 degrees Fahrenheit. That's like definitely hot enough to melt glass so you could make like bottles. I think that might be hot enough to forge steel, but maybe not. I don't think so. No, I don't think so. It's definitely hot enough to forge lead so you can make diving weights. I know that for a fact. 1,832 degrees could operate an internal combustion engine. Given the right plumbing. 1,832 degrees could easily cook some bacon. 1,832 degrees, that can do all sorts of industrial processes. Like, you can probably soften aluminum so that you can press it into these fancy shapes. You can almost certainly melt this weird plasticky glass that they use. You can mold a lot of the nuts and bolts and the guts of these machines. You can mold this plastic. You can do all sorts of stuff with 1,832 degrees. But instead, you go to your house, you take natural gas, which burns at 1,832 degrees, light it on fire, and then you blow air over it to raise the house temperature by 1 degree at night. Now that is inefficient because you've gone from very high quality 1832 natural gas to a very low quality output, 1 degree gain. Everybody know what I mean by that? You see, it would be more efficient to save that natural gas for making bottles and cooking bacon and internal combustion engines and industrial processing, and instead heat your house with like
Wood.
yeah, or like decomposing grass under a tarp. I know that's not practical, I'm intentionally being absurd, but if you could just take some grass clippings and wrap them in a tarp and let them decompose, that would heat your house by 1 or 2 degrees. That would not make bottles or cook bacon. So that would be more second law efficient. Watch me. It's about matching the quality of your output to the quality of your input. Yes, these make sense? Coincidentally, this is one of the stupid things about our fossil fuel economy. We use extremely valuable resources to make extremely low value outputs. You could say that we are squandering high quality, limited volume fuels to do really stupid, lightweight, trivial outcomes. I mean, you can use sunlight to make your rice. Solar cooker thing. Okay, questions about this? Because a few hands came up and I skipped them. Yeah?
What are the first law of efficiencies of common end uses of energy? Like the last question.
So I would challenge you to look into a few of these because I'd like more. There was a few examples in your book. Cars operate at about 10%. Incandescent light bulbs at about 5%. Plants at about 15%. Yeah.
But when it says what makes water and space heating such easy targets for energy efficiency improvements?
Because water can be heated with a lot of lower quality sources like sunlight. And spaces can be heated with lower quality sources. They're easy targets because these are low quality outcomes where we can cut out the high quality inputs. Does that make sense?
Yeah.
If you don't have questions, so you don't, I'd like to move on to number 13, which please look up. It's possibly one of the most cluttered and important diagrams in the class. Yeah.
212.
Yeah.
Okay, so if a this is like the most confusing thing ever.
Okay.
I always see like watts on a light bulb, where it's like 100 watts. It's like, well, what does that mean? So the book defines a watt as like a joule, like every second. Does that mean that a watt is like innately including a unit of time in it?
In other words, it's a flow rate. I'm not good at this, but that's one of the things where woods will just like blow your mind. Amperage, voltage, wattage. One of them is like the size of the pipe, and the other one is how quickly things move through the pipe. And I just forget, because I don't do this all the time, but you'll go, oh, you know, it's like this, and like that. And you'll be like, oh, it all makes sense. Yeah, but I think wattage is a flow rate. Yeah, per second. You're right. So the machine won't function without a certain flow rate.
So it's the energy going into the light bulb, not like the energy coming out of it? Like,
Yeah. All right, now, number 13, please look up. This is the part where you probably want a whole sheet of paper, or at least half a sheet. And you almost certainly want to label it U.S. Energy Budget. And this information, I'm going to help you read the diagram. I'll organize it in like 5 different lumps. I want to talk about 1, 2, 3, 4, 5 topics here. You're going to make, assuming that you want to have good notes, you're going to make a bunch of separate little clusters of how we interpret this. I will speak every number you need, but you got to get ready to write numbers and words. And before we start, I'd like to show you what you're looking at. Please look up. These are the sources of energy in the United States, where they come from. A transformation of energy, where we go from certain forms to other outputs. So there's an energy transformation here. And these are the uses, the users, the end users of energy, with a final analysis of how much is overall used and how much is overall lost in the system, based on 100 units. So these are percents in the United States. And just so you know, these are outdated. Every year they change a little bit, and there's a little politic and a little science. People can argue how we measure them. Because one way to measure is how much is produced, another way is to measure how much is delivered, another is to measure the efficiency of the delivery and the production. So people will kind of argue these numbers. Whenever you hear people having an argument, keep in mind that's kind of a political and kind of a scientific conversation. Here we go. Let's get ready. First, I'd like to break down the American sources of energy. Okay? You all realize that hydroelectric is dams that make electricity? You know how that works? Water comes through the dam and that spins a turbine to generate electricity. Have you heard of this? Hydroelectric? Okay, here we go. Hydro 2.7. Biomass 2.8. Geothermal 0.3. You'll eventually need all these, so you should definitely write them all down. Wind 0.15. And FYI, that's the fastest growing sector in American energy. Wind is America's fastest growing energy sector. Solar 0.01 or less. That number's growing. It could be a bit more than that. Nuclear. Could everybody please say nuclear for me?
Nuclear.
Now everybody say nuclear.
Nuclear.
Okay, that's not the word. Now everybody say nuclear. That's the word. No.
It's not nuclear.
It's like nuclear.
Nuclear.
Yeah, nuclear.
Nuclear.
No. Not that one.
So not Palin,
Not that
but
one.
more Bush.
That's okay.
Like
What? Yeah.
Like nuclear.
All right.
So more like Bush, less like Palin.
Nuclear.
No.
No.
Other way around?
Bush is the one who said nuclear.
Yeah.
So where do we get geothermal energy?
Nami, hi. We'll look at all these later. Nuclear is 8.1. Coal is 22.9. Natural gasola is 22.7. And petrol is 40.1.
Did you say natural gas is 22.7?
Yeah. Yes? 40.1. Uh-huh.
Why is solar so low when like recently everyone's been getting solar?
Doesn't produce that much energy, right?
In comparison, it doesn't produce very much.
This is one of those interesting analyses where our solar capacity is far greater than our nationwide solar generation. At any given time, about 0.1% or like one or whatever small number of America's solar panels are actually generating electricity that's being used. Because they'll make electricity when nobody's buying. They'll make electricity that just floods the grid to lower the usage of others. It's generation, I guess, probably. A lot of that is used off the grid where it charges batteries and never becomes useful because batteries are so inherently inefficient. And so this is one of those funny things about capacity and measurement. Solar power taps are like 10% of America's electricity. It's like, no, it isn't. And don't forget that this is all energy, so some of this goes to electricity, but there's a lot of other energy uses. But it's a pretty small amount. That number has grown. This is outdated. You get me a 2014 energy budget, it'll be much more solar. They're just not as pretty as this diagram. Now, we could break that down a little bit. Everybody got those numbers written down?
It's 42.1, right? Or 40.
Oh, 40.1. Now, if you look at the bottom three, fossil fuels make up roughly 86%, 85.5% of America's energy budget. We're trying to bring that number down. So maybe, hopefully, possibly, someday we'll get that down to like 80% in your decade. And maybe 70% someday soon, maybe. But a fundamental fact you must know. A significant majority of America's energy is fossil fuels. You know, global warming, air pollution, climate change. Sometimes unsavory political relationships. Allegations of military confused priorities. Over 85% of America's energy is fossil fuels. That's a lot. Those run out. We can dispute how much and how many are left and how excitingly we've reached more of them now, but they are finite. And nuclear, not nuclear, nuclear is not much better. It has a separate set of environmental issues, not the carbon. Nuclear fuel is finite. Maybe more, maybe less, different conversation. And that's another 8%. So here's another way to look at our budget. 93% of our energy sources are finite, non-renewable. We're running out of about 93% of our energy sources. That's an important thing to consider. We run our economy and roughly an equal percentage of the global economy on energy sources that are running out. Now, some people say, oh my God, they already run out. And some people say, don't worry, we got 200 years, but whatever, we only got a certain number of years. You know, you're living in a sealed shed and you're going through the food supply. Sooner or later, you're going to run out. So look at another analysis. When you add the hydroelectric, the solar, the biomass, the wind, and the geo, maybe roughly-ish 6% of our energy sources are renewable. Not going to run out. Seems good. Yeah, we can stop now. Good. Pretty much. Science is over. That makes what? About... yeah, bad. One thing I want to mention is that hydroelectric, that 2.7 at the top, that's renewable in the sense that the baby Jesus was always going to make rain. But it's not exactly renewable in the sense that those dams aren't going to last. In the 100-year plan, there's no running dam. Just so you know, we don't build dams anymore in this country. Most of the world has stopped building dams, except for a few developing nations. And hydroelectric power, it's nowadays just too expensive and not a good enough investment. They run out too quickly. They die too fast. So yes, the baby Jesus rain is renewable. But no, the dams are not long-lived. Everybody bored with my conversation about renewability? Good. Next. Please look up here. I'd like to throw out another little cluster. Now we're going to talk about electricity. So if you want, you can draw a line and go, electricity. "38% of our energy sources are used to make electricity." That's mostly coal. You can see it in the diagram. Nuclear goes to electricity. The black line is the coal. Look at how much of that goes to electricity. And a little bit of natural gas also goes into electricity. There are smidgens of other electrical sources. But if you look at the size of the bars, most of our energy used for electricity production is coal. Now, there's this thing I got to talk about in electricity, which is unfortunately, like, I've never figured out how to make it really simple. And so I would recommend that you make, like, a little bit of notes and then a little bit of notes and then a punchline. And I'll try to identify those when I talk, okay? But I want everybody to please try to follow with me. I have a diagram that you don't really need to draw yet because later in the unit, I'll give you a much more detailed diagram. So I'll explain the process later. You're going to get more detail for this explanation. Sam, you find any good diagrams, bud?
Yeah, 2013.
Thanks, Zombie. Throw me a whole bunch of them via email, please. Or on a folder or something like that. All right, check this out. This is a horrific simplification of how we make electricity. And like I said, I've got a whole lecture with examples and visuals. There's a little bit of physics behind this, just a little bit. But with one exception, all electrical generation methods, coal, natural gas, petroleum, hydroelectric, nuclear, everything is just somehow make steam to spin a turbine to make electricity. And I'll explain that later, so you probably read that diagram. But the fundamental concept is use an energy source like nuclear decay or burning coal or whatever. You could burn people, and you could burn sticks, you could burn car, I don't care. Burn whatever to boil water, and that steam will spin a turbine, and by spinning the turbine, you make electricity. Okay? We'll explain that later. But at this point in the game, I want to talk numbers. Because you know, no system is perfect. Everybody knows, right? In any transformation, some is lost. Remember we talked about that? First law? Right? So watch this. I'm going to introduce a couple of variables, and you're going to have to write something down now. In electrical generation, if you're putting in 100 units of energy, 33% is lost as heat, 67% is made into electricity. 1/3, 2/3.
They're putting in 100 units of energy?
Yeah, so given 100 units of starting energy, 1/3 becomes heat, 2/3 becomes electricity. That's the average American generation efficiency. So I don't know how you're writing what you're writing, but in the electricity section, the average American generation efficiency is 2/3. The average American generation efficiency is 2/3. We get about 67 units of electricity from 100 units of fuel. That's an average with nuclear and coal and leaves. And then, please look up, that electricity gets pushed through wires until it reaches your sad house. And remember that wires are like a crowd that you're trying to run through, so there's a little bit of conflict, and it's not a perfectly efficient system, so please look up. Of those 67 units, 1/2 are lost as heat. Only 1/2 of that is delivered electricity that reaches the end user. 1/2 is heat, 1/2 is delivered.
Gross energy delivered electricity.
Electrical energy. Like the stuff that comes out of your wall outlet. And so, this is a first law efficiency. We're talking about amounts. I'd like everybody to please follow me on this math, because this is kind of the big punchline here. We're going to do 2 separate math steps. I need everybody to keep track of the money. Okay? You start with 100 pennies. 33 are wasted as heat in generation. How many did that leave you? 67, right? Are we okay with that? Now, of those 67 pennies you've got left coming out of the power plant, 1/2 will be lost as resistance heat. So how many pennies reach the outlet in the house? About 33-ish. In other words, from generation, transmission to the end user, 1/3 of energy becomes useful electricity, 2/3 is lost. 1 kilowatt at your house was 3 kilowatts of fuel at the power plant. Yes?
When we're paying our electric bill, do we pay for the 3 kilowatts?
Basically, they're all built into the system. It's not like people are losing money to give you electricity. So if we could make this efficiency 100%, which is impossible, right? If we could get perfect translation of energy to electricity at the Mel House, we could remove your electrical price by 67%, which is the waste in the system that you're still paying for. Now, I want everybody to look up. We're back to the numbers. Of that 38 units of America's energy budget that go into making electricity, keep in mind that only delivers 12.5 to the end user. The other 25.5, that's just heat loss. That's just cooking the air. Which I find to be pretty shocking. I mean, if you look up there, does everybody see that huge gray line coming out of electricity? That's the primary energy waste in America. Generation and distribution waste. The number one American energy loss is generation and distribution of electricity. Look at the size of that gray bar. A quarter of America's energy budget is heating the atmosphere because there's inefficiency in the grid. You see, 8 years ago, you guys were all like pooping on your pacifier. But when Barack Obama was elected to the presidency, he nominated 6 years ago? Yeah, whatever. You're still pooping your pacifier. He elected like a really famous scientist dude to head the energy department. And like one of his first public speeches was, we are strangled by our inefficient electrical grid. Like one of the top presidential priorities when Obama started his presidency was fixing up the grid so that we could shrink that big gray line. I mean, think about it. That big gray line, that's all CO2 we're making. That's all global warming we're causing. That's all air pollution that's for no reason. That's a huge inherent inefficiency. And the last thing you might want to write down in the electricity part. If you can save 1 unit of electricity at your house, you're saving 3 units of energy at the power plant. That's one of the reasons it's such a priority to get people's houses to be super efficient. Not because we really give a crap about your kilowatt, but because that's triple the kilowatts in the energy source. Everybody like that conversation? Are we good with the electricity part? Anybody want to ask me anything about the electricity part? Yes?
There was like a last statistic that you said. What was that?
What was it? What?
Last statistic that you said.
That for 1 unit saved at your house, you've saved 3 at the power plant?
No, there was another percentage, something to do with like 10, 20%.
I just like opened my mouth and channeled the Jesus.
Just go on YouTube.
I have no idea what I'm saying, bro. This is the peyote talking. Yeah.
So, is all that heat that comes from like the inefficiency in the grid, is that sort of negligible in causing global warming, or is it just sort of...
It is. I mean, when we talk about global warming, I think it would be negligible. I don't know how to quantify it, but I can't imagine it's comparable. Separate issue, though, is a very interesting one. That is primary in causes of the urban heat island effect. The idea that cities are hotter than their surroundings. And so urban heat waves are so deadly because when people are living in cities, it's very hard to cool the places down, and some people who are poor don't have access to cooling. And this is one of the primary reasons for that issue, the urban heating.